Greetings. Welcome to Orion Works. My name is Stephen Vincent Johnson. I hope you will enjoy your stay while I go about unraveling and demystifying the mysterious geometry of orbital mechanics. I hope my presentations will leave you with a more intuitive understanding of the subject.
Greetings. Our name is Stefanos Hal. We have been assigned the role of a sentient AI narrator who currently exists within a 17th century setting. We have been called into existence so that Stephen will have more flexibility in assembling and editing his thoughts and visions. We want to introduce you to a remarkable man who made significant scientific contributions in the 17th century. It's impossible to accurately describe the full essence of any historical figure, both in words or with the aid of advanced audiovisual technology. The best any presenter of history can do is describe as accurately as possible their accomplishments, as well as their failures. Doing so, we hope, will give the student of history an appreciation of the challenges any famous historical figure had to confront, and what they had to deal with within the impersonal annals of our short lifespans. We bring up for your consideration the name of Johannes Kepler. He was a German astronomer, mathematician, and astrologer. His notable works include his laws of planetary motion and his books Astronomia Nova, Harmonics Mundi, and Epitome Astronomiae Copernicani. These works greatly influenced the scientific community, including giants like Isaac Newton. Kepler's groundbreaking work laid an important foundation to Newton's theory of universal gravitation. We honor Kepler today for having played a significant role in establishing the scientific method, a rigorous approach to inquiry and study that continues to guide modern science today. Johannes Kepler was a key figure in the birth of the 17th century scientific revolution. In addition to his scientific pursuits, Kepler was a university mathematics professor. He was also a popular astrologer. He earned a significant portion of his income from casting astrological charts for clients. Astronomy and astrology were closely linked, and the process of separating these two disciplines was just beginning. The analysis of astrological events was often perceived to possess more value than analyzing astronomical events. Most considered the study of astronomy a subject best left to the predilections of astronomers. While debates may still rage on, today, astronomy tends to be regarded as possessing more relevance than astrology, especially within scientifically minded circles. Our focus here is not on a debate between astrology and astronomy. We shall concentrate on Kepler's laws of planetary motion and their impact on scientific investigation. If Kepler were alive today, what would he think of his three laws? Would he want to revise them to better reflect the accuracy of 21st century findings? Would his laws continue to align, or would they contradict our current understanding of planetary motion? We bring this question up as a forum of speculation because Johannes Kepler, if anything, was a stickler for accuracy. Before offering up what we speculate Kepler would change or update, we should begin with a brief history of what led to Johannes Kepler's groundbreaking discoveries. Kepler spent much of his time thinking about the solar system and contemplating the true shape of Mars' orbit. He preferred the heliocentric model where planets orbited around the Sun over the geocentric model where all the planets orbited around Earth. In Kepler's time, it's important to keep in mind the fact that the Church supported the geocentric model. They considered challenging this belief a blasphemous act, the consequences of which many astronomers were well aware of. Kepler also questioned the belief that planets orbit in perfect circles as Nicholas Copernicus had proposed. To resolve quandaries on such matters, Kepler knew he needed accurate data on the astronomical coordinates of planet Mars. Kepler was convinced the data he needed to resolve his conundrum existed in a highly detailed table created by the well-known Danish astronomer Tycho Brahe. To this end, Kepler focused his efforts on becoming employed as Tycho's assistant in order to gain access to his Martian data. However, Tycho was very protective of his tables and only metered out small portions of data each time Kepler made another request. This increasingly frustrated Kepler to no end. Tycho also was championing his own theory of the configuration of the solar system, the Tychonic system, a system he wanted Kepler to publicly support. Tycho's system placed Earth at the center of the solar system where the Moon and the Sun orbited around Earth. What might be considered audacious about Tycho's system, particularly from a 21st century perspective, was the fact that all the other planets, Mercury, Venus, Mars, Jupiter, and Saturn orbited around the Sun while the Sun itself continued to orbit around Earth. History shows that other astronomers developed similar configurations before Tycho's Tychonic system was created. In the 5th century, a jurist, polymath, and Latin prose writer named Johannes Kepler, who was from Madura, Algeria, described a modified geocentric model. As in Brahe's model, Kepler modeled the Earth as positioned at the center of the universe with the Moon and Sun circling Earth. Also, as in Brahe's model, the two inner planets Mercury and Venus circle the Sun. What is different from Brahe's model is that Kepler places all the outer planets, Mars, Jupiter, Saturn, and the stars, as circling around Earth, whereas in Tycho's model the outer planets are orbiting around the Sun rather than Earth. While Brahe had assigned Kepler to complete a historically famous star catalog called the Rudolphine Tables, he also wanted Kepler to publicly back his geoheliocentric Tychonic system rather than Copernicus' heliocentric system. But Kepler had his own theories he wanted to pursue. Inevitably, their differences in opinion caused friction in their working relationship. In the midst of this conflicted relationship, fate intervened. According to a first-hand account given by Kepler himself, Tycho, who had been attending a banquet in Prague, apparently chose not to excuse himself in order to relieve his overextended bladder. Tycho apparently felt that leaving the hall in the midst of ongoing ceremonies would have been an unbearable breach of etiquette. Soon afterwards, Tycho suddenly fell ill. He contracted a serious bladder or kidney ailment. Days later, as Brahe laid in bed dying, he summoned Johannes Kepler to his bedside and urged him to complete the Rudolphine Tables. He also expressed a hope that Kepler would promote his own Tychonic planetary system, and set aside the heliocentric system developed by Nicholas Copernicus. How Kepler responded precisely to Brahe's final wishes appears to have been a private matter not meant for the eyes of history to record. 11 days later, the ailment killed Brahe. In the immediate chaos that followed, Kepler realized a unique opportunity was presenting itself to him. He acted quickly and discreetly. Kepler absconded with Tycho's Martian tables before Tycho's heirs got around to securing them for their own self-serving purposes, a purpose Kepler was sure would not have been in his favor. Inevitably, Kepler's sudden total possession of the Brahe's tables was uncovered, and the legal disputes that ensued took years for Kepler and the Tycho estate to settle, particularly in the financial sense. But in the greater scheme of things, what mattered to Kepler was the fact that he finally acquired complete and unfettered access to all of Brahe's highly accurate astronomical coordinates, particularly the coordinates of Mars. For Kepler, the questionable act of theft was worth the ensuing years of legal and financial wrangling and headaches it inevitably produced. Kepler's meticulous analysis revealed the fact that Mars' orbit was not a perfect circle. The orbital coordinates bowed inward as if taking on the shape of an ellipse. But ironically, Kepler initially did not experiment with the ellipse. He had assumed that the Greeks would have documented such a fact had they found elliptical orbits to be true. It left Kepler pondering what other geometric shape might be involved. He ultimately settled on the shape of an oval. He tried fitting Mars' orbit to an oval shape, and tried 40 times, to no avail. Then, on a hunch, he decided to try the ellipse.
Johannes!
And voila!
Use the ellipse!
An ellipse turned out to be a perfect fit. Apparently, the Greeks had never gotten around to investigating the matter. One can well imagine what Kepler must have felt having spent 40 futile attempts trying to fit Mars to an oval-shaped orbit. It brings to our attention an ancient Russian proverb, when translated to English means, "Trust but verify." The phrase became famous in the United States when President Ronald Reagan discussed nuclear disarmament with the Soviet Union in the 1980s. Kepler learned a valuable lesson about following the scientific method, the perils of not verifying preconceived assumptions of the presumed investigations of others. Kepler went on to prove that planets do indeed orbit the Sun in elliptical paths. He also discovered that the Sun is centered at one of the foci of two foci belonging to the geometric architecture of the ellipse. In the history books, this became known as Kepler's first law. He also went on to prove that a line joining a planet and the Sun sweeps out equal areas during equal intervals of time. In the history books, this law became known as Kepler's second law. He published his findings in the book Astronomia Nova in 1609. Kepler went on to document a third law, but that is a matter for a future presentation. Let us now return to the 21st century and bring Johannes Kepler along with us. What would Johannes think about his first law? Would he believe it has stood the test of time? We think he might be quite troubled. As previously mentioned, Kepler was a stickler for accuracy, and today, he would notice that while most textbooks accept his first law, as is, it isn't entirely accurate by modern standards. So what's wrong with Kepler's first law? The issue is the part that describes the Sun as being fixed at one focus of the elliptical orbit. In graphic terms, Kepler essentially superglued the Sun to the center of one focus. However, we now know that the Sun is also moving, just like Mars. Since the Sun is not stationary, it can't be superglued to a focus. This raises the question, if both the Sun and Mars are moving, what are they orbiting around? Would it be the same point for both, or would there be two unique points placed in different locations? The most direct answer is that both Mars and the Sun are orbiting around a focus. But whose focus are we talking about? Is it the same focus as before, or something completely different? We now understand that a more accurate version of Kepler's first law would reveal a unique symmetry. To observe this symmetry, we need to consider Isaac Newton's discoveries. Newton, born 13 years after Kepler died, developed the law of universal gravitation. This law states that every particle attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. We must apologize here as we realize this statement is quite a mouthful for many to digest. Simply put, the Sun attracts Mars in the same way that Mars attracts the Sun. Also, the closer the distance is between the two objects, the force of mutual attraction increases exponentially. To understand how Newton's law affects their respective orbital shapes, we must consider the masses of the two objects. We especially need to consider how their masses might differ from each other. Incorporating these details into the construction of their individual orbital paths reveals a poetic dance both objects perform in tandem with each other. This dance swirls around a specific point in space called the center of gravity, or center of mass. The center of gravity was a fundamental concept first studied by Archimedes of Syracuse, a Greek mathematician who lived from 287 to 212 BC. We can easily demonstrate the center of mass with a typical playground seesaw. Recall the joy and excitement we felt as kids playing on a seesaw, swooping up and down, and occasionally falling off. Our seesaw faithfully follows Archimedes' law, which obeys a simple mathematical formula. Where is this center of mass located? If you would prefer to skip some high school algebraic terms, feel free to skip forward about 4.5 minutes to the next section. Doing so should not adversely affect your overall understanding of the basic changes Johannes Kepler would make to his laws of planetary motion. As for those who enjoy a little bit of algebra, you may appreciate the following mathematical breakdown and demonstration. We need to incorporate this mathematical formula, known since Archimedes' time but not fully comprehended in Kepler's time, as it plays a crucial role in shaping the orbits of planets and the Sun. It took another half-century after Kepler's time for its significance to be recognized, thanks to Christian Huygens, Isaac Newton, and Edmund Halley. The formula takes into account the respective masses and positions of two objects. It is a simple fraction involving a numerator and a denominator. In the numerator, we multiply the mass of the first object by its position in space, then add that value to the second object's mass multiplied by its position in space. This resulting value is the numerator. We then divide the numerator by the sum of the two objects' masses, which is the denominator. The resulting value is the center of mass of the two objects. We will demonstrate how the center of mass changes depending on the masses and positions of the two objects. We will duplicate two horizontal line segments as if displaying two one-dimensional lines displayed on a flat two-dimensional graph. At the left end of the segment are two yellow dots representing the first mass, mass 1. At the right end are two green dots representing mass 2. The two yellow dots and two green dots represent planets or suns. In the middle of the two light gray horizontal lines are two red dots representing the current position and center of mass for both points. We will start with both masses being the same amount, represented as 50 units of mass apiece for a total mass of 100. The location for M1 starts with the position value of -10, the leftmost end of the line segment, whereas the location of M2 starts with the position value of +10, the rightmost end. Again, notice the red dot, the center of mass positioned in the middle of the line segment between the yellow and green dots. Its position would be an example of a horizontal seesaw perfectly balanced in mass at both ends. If we change the position of mass 1 to 0, the origin point, while leaving the position of mass 2 at 10, notice how the upper line segment has shifted to the right. It has also shortened its length by 1/2 its prior length. But notice the red center of mass point remains precisely centered between the yellow and green dots. Meanwhile, the lower line segment remains stationary at the center of mass position, while both segment lengths have shortened by 1/2. As expected, both the upper and lower segment lengths remain the same length. If we now move positions M1 and M2 to the opposite end, the left end of the line segment, -10 and 0 respectively, the center of mass ratio continues to be maintained in the middle between the yellow and green dots. Also, no changes are noticed in the lower segment. We will now return the yellow and green dots back to their original maximum distances apart, that being -10 and 10 respectively. We will keep the distances fixed while we change the respective masses of M1 and M2. Let's lower the mass of mass 1 from 50 down to 10 and increase the mass of mass 2 from 50 to 90. Notice how the center of mass shifted to the right, towards mass 2. This is precisely how a seesaw would behave with two individuals sitting on a seesaw, where the left individual weighed 10% of their total weight, while the right individual weighed 90%. They would have to reposition the axis of the seesaw to the same location in order to balance their wildly different masses. If we switch their respective masses, notice how the center of mass shifts to the left towards mass 1, which now has a mass of 90, whereas mass 2 now has only a mass of 10. Again, just like on a seesaw, the center of mass must be repositioned accordingly. This is a crucial mathematical tool needed to update Kepler's first law to fit 21st century standards of astronomical accuracy. In the previous demonstration, the animated graphic consisted of a simple rigidly fixed one-dimensional horizontal line segment. We need to transform our stationary horizontal line segment back into the realm of 2D space so it can dynamically rotate or spin on its axis, the axis being the center of mass between the Sun and planet. Relatively speaking, we observe the center of mass as a fixed and stationary position relative to the dynamically changing positions of the planet and Sun. This was something Kepler could not have uncovered in his 17th century time period. The astronomical coordinates Kepler extracted from Tycho Brahe's tables were not precise enough to detect the subtle perturbations the Sun was engaged in, as all the planets in the solar system, each adding their own influence, orbited around it. Therefore, from Kepler's analysis, the Sun appeared to have been fixed, as if superglued to a focus belonging to the elliptical orbit of Mars. But had Tycho Brahe's tables been sufficiently accurate, we suspect Kepler, being the stickler for accuracy as he was, would have taken the Sun's orbit into consideration. Kepler's first law would have been transformed in a subtle but groundbreaking way. Kepler's first law would not have positioned the Sun at the center of one of the two foci of Mars' ellipse. Kepler would have realized that there was not one ellipse, but two ellipses in play. One ellipse belonged to the orbit of Mars, the other to the Sun. Kepler would have also noticed that the two ellipses were intimately intertwined. It is helpful to explain some basic concepts related to the geometry of ellipses. Their eccentric shapes, meaning how round or flattened the ellipse appears, are described numerically as a fractional number. We categorize the shape of ellipses by giving them an eccentric value that is greater than or equal to 0, but less than 1. An eccentric value of 0 indicates a perfect circle. A circle is a special case of an ellipse where its two foci are positioned at the center. In a perfect circle, the radius length remains constant no matter the direction from the center. An eccentric value greater than 0 results in the separation of the two previously fused foci. In a sense, the foci individuate from each other. While still intimately connected to each other, albeit from afar, they are now capable of taking on different functions. This is especially the case insofar as the geometry of orbital mechanics is concerned. Calculating an eccentric value is easy to visualize if we set the radius of a perfect circle to 1. As we flatten the circle to create an ellipse, the positions of the two foci change, resulting in a fractional eccentric value. The horizontal length of the major axis remains constant at 1, while the vertical length of the minor axis starts at 1, that is, when the eccentric value is 0, and decreases towards 0 as the eccentric value approaches 1. We apologize again as our most recent verbiage may have sounded a bit too turgid for many to follow. As compensation, we will present you with a brief side comment that may amuse some of you. We bring to your attention two unique ellipses. One has an eccentricity of 0.8, and the other one 0.6. Notice that their respective minor axis values share the same eccentric numbers, except that they are switched. For demonstration purposes, most of the ellipses visualized in this presentation have been set with an eccentric value of 0.8. Besides being a pleasing shape for an ellipse, its minor axis length value generates a simple to understand fractional value. It's advantageous to employ numerical values that generate simple to comprehend fractional numbers. This is often done, particularly when trying to explain geometry or a complex mathematical equation in order to make its function more digestible for the student. Otherwise, the teacher and student risk treading dangerous waters where we can end up crunching fractions that will only complete at infinity. Simple numbers tend to be easier on the eyes as well as with the processing capacity of our brains. But wait! There's more! As previously mentioned, we have two ellipses whose eccentric and minor axis values are easy to digest. They both use simple fractional numbers of 0.6 and 0.8 that are essentially interchangeable with each other. Perhaps you might be wondering, why is this so? Perhaps these two elliptic values are geometrical riddles the universe created to do nothing more than temporarily confuse mathematicians, where many might be wondering if they had gotten their eccentric and minor axis values mixed up. Be this as it may, it should not surprise you to learn that the elliptic area shared between these two ellipses has become known as the Bermuda ellipse, and few mathematicians speak willingly or openly about it. And if you believe this, can we interest you in purchasing Bermuda? Let us leave the Bermuda mystery behind us. Our goal has not been to suggest that 21st century astrophysics has rendered Kepler's first law obsolete. Rather, modern astrophysics has expanded on Kepler's original insights, developing new terms and definitions that offer a more accurate understanding of his findings. Today's astrophysics reinterprets Kepler's use of the Sun as the center of orbital motion with a concept called the barycenter. The barycenter is an abstract but distinctly locatable fixed point in space and time. The term is essentially synonymous with the term called center of mass. It represents the shared point around which two celestial bodies orbit each other. By introducing the barycenter, astrophysics has redefined the Sun's role as no longer holding the Sun as the absolute center that dictates the elliptical orbit's shape. Modern astrophysics has revealed that there are not one, but two orbits, one for the planet and one for the Sun. Despite these advances, there still seems to be a lack of recognition that the barycenter concept could easily be integrated into an updated 21st century interpretation of Kepler's first and second laws. While Kepler would have named it differently, this stationary point in space aligns with the role he assigned to the Sun in his original laws. One aspect of contemporary astrophysics that often goes unnoticed is that both the Sun and planets have elliptical orbits that share a common focus. According to a contemporary reinterpretation of Kepler's first law, both Mars and the Sun follow unique elliptical paths that mirror each other symmetrically. Each orbit has two foci, which they share one with, uniting at a single point in space and time, what modern astrophysics refers to as the barycenter. By sharing this focus, the two distinct orbits and the celestial bodies that follow them remain deeply interconnected. When two celestial bodies orbit each other, their orbits share the same eccentricity regardless of shape. This eccentricity can range from 0, a perfect circle, to 1, which flattens the orbit into a one-dimensional line. Regardless of their sizes or masses, from the perspective of their shared focus, the barycenter, the two bodies are always exactly 180 degrees apart from each other. Next time you look up at the stars and planets in the evening sky, consider that two orbiting celestial bodies can remain intertwined forever. These two-body orbits are one of the most stable principles in astrophysics. In fact, binary orbits are surprisingly common across the universe. It's estimated that 70 to 80% of larger, more massive stars in our galaxy have binary partners, a figure that nears 100% for the hottest, most massive stars. Among red dwarfs, about 20 to 30% are in binary systems. Even some 15 to 20% of asteroids between Mars and Jupiter share binary orbits. Planets, too, can form binary pairs. For example, Pluto and its large moon Charon form a double-planet system. Our Earth and Moon are sometimes described as a double-planet system as well. But technically, they aren't because they're shared foci. The barycenter lies within Earth's diameter. To be a true double-planet system, the shared foci must lie outside the diameter of both bodies as it does for Pluto and Charon, thus granting them a distinct status within our solar system. Despite such stability, as with many things in our dynamic universe, nothing is permanent. A stable two-body relationship can be disrupted by the influence of a third body or several nearby objects. Occasionally, an additional body might wander into this stable arrangement, altering or destabilizing it. Sometimes, one of the bodies might collide with others, causing spectacular explosions. Their stable orbits are forced to readjust. They try to find a new balance, or else they are forced to go their separate ways. Given enough time, just about every stable two-body problem will eventually encounter random outside events. Eventually, the universe will change even the most stable of relationships. While chaos seems to reign, researchers over the centuries have discovered special case configurations where islands of orbital stability exist for the three-body problem. These rare configurations seem to defy the universe's tendency to choose chaos over order for the vast majority of three-body configurations. Their choreography reveals complex patterns that are both sophisticated and beautiful. We are approaching the end of our presentation. We wish to leave you with a thought of dreams similar to the ones Johannes Kepler may have experienced as he completed what many have considered to be the first published work of science fiction. He titled his story Somnium, which means the dream, in Latin. Kepler's story follows a young Icelandic boy named Duracotus, whose mother is a witch. Possessed with the powers of a witch, she summons a demon in order to transport her son and herself to the moon. Standing on the lunar surface, they observe the Earth. With the demon's help, Kepler vividly describes the moon's harsh environment. The story speculates on what it would be like to live there. Somnium was Kepler's way of explaining and defending the work of Nicholas Copernicus, specifically the theories of celestial mechanics, planetary movement, and the heliocentric universe. The novel is remarkable for its early exploration of space travel and the extraterrestrial perspective. Unfortunately, Kepler's imaginative story nearly got him in trouble with the church because of its fictional depictions of witches and demons casting strange spells, including the power to transport people to other worlds. Fortunately, Kepler managed to avoid punishment. However, he had to spend significant time and effort writing extensive explanations to reassure his critics that his work of fiction was not intended to deceive. Kepler's imagination, combined with a strong penchant for geometrical accuracy, allowed him to envision a more accurate display of how all heavenly bodies perform their intricate choreographies. His curiosity and unrelenting drive for the truth have earned him an honored place among the greats of our civilization. Kepler was instrumental in creating a new paradigm of investigation by applying the scientific method, a methodology for finding the truth that our civilization has used for centuries. But Kepler was more than just an excellent astronomer who followed the scientific method. He possessed the ability to imagine celestial events and the nature of how the universe interacts in ways most of his colleagues were unwilling or afraid to investigate, particularly with the threat of imprisonment looming over their lives. Kepler knew the risks he was taking, but he did not allow such fears to bury his dreams or be held hostage to the prevailing religious and philosophical dogmas of the time. For that alone, Kepler's work should remain an example of not only applying the power of the scientific method, but also the power to follow your dreams, no matter what treachery others may warn you against. So dream on, Johannes. Dream on, for we still honor you and admire your visions of the universe, both past and present, and perhaps even in the future, as well.